Hey guys, welcome back to another A-Level Maths video. This is starting probably one of the brand new topics in A-Level Maths, which is exponentials and logarithms. Now, exponentials isn't necessarily new, but logarithms certainly is. But there is quite a bit new with exponentials as well. But that's your kind of power laws. Just before we get started, just remember, link in the description for the worksheet that you can attempt at your own leisure. I'd recommend waiting maybe 24 hours or so. So within 24 hours, do it again. There's also, that's on Patreon, but remember it's completely free for you guys to download. There's also a link to the A-Level Maths playlist, which contains all the lessons I did, the live lessons I did last year. And of course, just wanted to let you guys know that on Patreon there's also a stats and mechanics course that's going to go through everything you need for stats and mechanics. And also, if you want to kind of book your tuition slot for the classes that are starting in September, then, or if you want to join them if this is after September, if you're watching this after September, then please feel free to email me, the link's in the description, or ask me on Discord. But without further ado, let's get into what the hell is a logarithm and an exponential. So with an exponential, you've actually already seen these before. They are your stereotypical power laws. If we draw little axes like this, again, it doesn't have to be super neat. Your power law, so a graph where you have something like a to the power of x, looks like this, right? And it goes exponentially off. And the idea is that it never crosses the y equals 0 line. It's something called an asymptote. It never crosses that. Now, this is actually a very common model. If you look at, for example, the stock market over the last 100 years, it has an exponential increase. The world GDP, the global population, the population of the majority of countries in their kind of growth phase, all have a growth like this. And there are plenty of other things too. Populations of all kinds of species and viruses and bacteria and all that kind of stuff. Now, what is an exponential? Well, an exponential is essentially just a power like this. However, there is one special type of power that you do need to know about, which is E. Now, what is E? E is just a number, and it's a number that's going to come up a surprising amount of time. It comes up a lot in kind of maths and physics and statistics and all of that fun stuff. And if you have a look on your calculator, it is a special letter here. Can you see this shift E? So if we just press that and we press e to the 1, it gives us a number like so. So just so you're aware, whenever you see e, you can treat it just like any other power. It's the same fundamentally as 2 to the power of x, or 3 to the power of x, or 10 to the power of x. They're all the same. Okay? It's just that e has a special value. It's kind of like pi in that sense. Pi is just a letter that we use to represent a really long number. E is a letter that we use to represent a very specific and long number as well. Okay? So whenever you see E, it just means the same as having a number here. You can treat it exactly the same, which means if, for example, you have, if you had 2 to the power of x times 2 to the power of x, if you remember from your power rules, you add the numerator, the powers, the indices. So x plus x would be 2x. It would be the exact same if you have e to the power of x times e to the power of x. You would have e to the power of 2x. Fundamentally is the same thing. Now, what the hell is a logarithm? Well, every single operation that we do in maths has an inverse function. A logarithm is the inverse function of a power. So, here's what this, if you remember, to work out if you want to draw the graph of an inverse function, it's actually just a reflection in this y equals x line. So the log graph actually looks like this. Like so. Okay? And that is something like y equals log of x. Let's quickly discuss all the different ways that I'm going to help you in your GCSE or A-Level Maths careers. First of all, I wanted to talk to you about the YouTube members. This is a really cost-effective way of getting tutoring. So I'm going to do weekly live streams for GCSE and A-Level Maths, and that all comes for £18 a month, and you get at minimum an hour of tutoring per week in these live streams. At the moment, they're quite small, so you basically get tuition for about £4.50 an hour, which is really, really cheap. The second thing is the Patreon. For those of you doing A-Level Maths, I have already completed AS Stats on my Patreon. It is a full course with worksheets, mark schemes, videos. I answer all the questions. We're going to do exam papers and everything that needs doing. We're halfway through mechanics as of yet. And lastly, there's tuition. I still have places in my group classes for A-Level Maths and GCSE maths. For GCSE, it's £30 an hour, and for A-level, it's £40 per hour. So if you want to let me know if you're interested, just email me or join the Discord where I'm very, very active all the time. Anyways, back to the video. If we go and find the log button on our calculator right here, it doesn't matter what the base is, I'm just going to put it as 10 for now. If I put in a negative number, it does indeed give me a math error, okay? And that's a really, really important fact for this. Likewise, if I put in 100, I get 2. Now, you might be spotting roughly what logarithms do. How, if I told you again that the inverse function of a power is a log, have a look what's happening. What it's basically telling me is this base to the power of something gives me 100, and it gives me what that something is. 10 to the power of 2 gives me 100. So what if I made this 1,000? What do you think it would be? Well, 10 to the power of something gives me 1,000. 3. So what if we changed it? What if we did base 2? Well, let's do base 2. And of course, if I did 2 to the power of something gives me 2, I get 1. 2 to the power of something gives me 4, I get 2. 2 to the power of something gives me 64, I get 6. So what it does is it tells you what power you need in order to get a certain answer. And that's essentially all a logarithm is. Now, of course, it's not that easy. Of course it's not that easy. Because we have a bunch of rules that we get to use. I know, exciting. We get to do a bunch of different stuff with it. And I'm going to write down some of the rules now. Not all of them. If we remember our power laws, and we're going to have our, I'm going to call them log laws. If we times two powers together, you add them, right? So if you have a to the power of x times, and it have to be the same thing, a to the power of y, you get a to the power of x plus y. And the corresponding rule with logarithms is that if you add two logarithms together, so log a plus log b, is the same as having log of ab. By the way, just so you're aware, in maths we don't always write a base. Now, the reason for this is if they just write, so normally you'd have log to the base 2 of 4 equals 2, right? Something like that. You have to have a base. However, if you ever see log of a number, that is the same as writing log to the base 10 of that value. The reason for this is our number system, if you weren't aware, is base 10, right? We have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So a lot of the time, when we use logarithms, we use log to the base 10. So over time, we've kind of started omitting the 10. So if you ever see log of something, it means log base 10. Okay, and that's just to kind of, again, if you're talking about the GDP of the world, or you're talking about a population or something like that, it just helps you. 9 times out of 10, you're going to be using log to the base 10. Likewise, if you ever see ln, something called the natural logarithm, that is the same as having log to the base e, which again, it comes up quite a lot. And yeah, it's just called the natural logarithm, it's called ln. So if you notice on your calculator, we have ln over here. And on some calculators, they do have a log base 10 button. But I don't believe, yeah, here. So if you look, shift, log. So if I do log that, if you remember log base 10 of 100 should be 2, log 100 is 2 as well. Cool. So yeah, for these rules, I'm not going to bother writing the base because, again, it just applies to any base. It could be ln, it could be log base 2, whatever. Now, what about dividing? Well, if you remember, if you have two powers, again, they have to have the same bases, are divided, you do a subtraction. And what happens when you do the same thing here? Well, it's very similar. You're going to notice a lot of similarities. Right? So it kind of works backwards. If you look here, we start off with two things timesing each other and end up with them adding. With logs, we start off with two things adding and they end up timesing. With here, we end up with two things dividing and they end up subtracting. We start with two things subtracting, they end up dividing. Can you see how it's just opposites? Okay. Some of these are a bit wonky. So what I will, another thing I will point out is, for example, if you have a to the power of x to the power of y, you would then have a to the power of xy. And it looks a bit different on logarithms. So if you have log to the base a, but to the power of b, instead, that thing just comes to the front, like so. So I guess you could say it's somewhat similar. We're kind of going backwards in the same way. We start off with this and end up at that, kinda. But yeah, it's slightly different with that. So, there is one more thing that you need to be able to do, but I'm going to show you via examples and questions because I think it'll make a bit more sense. In terms of using these, what you can do is write these down on a piece of paper when you do this worksheet, and then that way you'll learn over time which ones you need to use. But I would recommend having on a separate sheet instead of kind of scrolling up, scrolling down and all that kind of stuff, flipping backwards and forwards on paper. So now I want to give you a few questions. Now this one should be fairly easy. 2 to the power of what gives you 32? You don't exactly need to use a calculator for that, but if you wanted to, you could just put log, you want a base of 2, and your answer's 32, and that'll give you the answer. However, that isn't always the most obvious thing. So for example, here you have 3 and 13. So again, if you are kind of clued on with the definition of logs, you can just do something like this. However, how are you going to know you're right? There isn't much working out there. Now, I will say that this will 100% work, but let's see mathematically how we get there. So, I mentioned that exponentials and logarithms are inverse functions of each other. Now, when we solve algebra, let's say we had something, let's keep it simple, 2x equals 12. How would you solve that? Well, what you do is you do the inverse function of whatever's happening to x. So in this case, we have 2 times x. So what's the inverse of times? It's divide. You do the same thing when you have algebra like this. So here we have a power. And what's the inverse function of an exponent of a power? It's a logarithm. So what we can do is apply a logarithm to both sides of the equation. I know this sounds a bit weird, but watch this. So I'm going to give it the same base for a very special reason. Right? If you want, you can put the x on the inside of the brackets. Either way, it's fine. And remember, whatever you do to one side, you do to the other side. Now, going back, I'm going to use this power law to bring this power x to the front. Okay, now you can use a calculator to work this out. And you know what? That's exactly what I'm going to do. What do you think this would be? So before I go through it, have a think, 5 seconds. What do you think this answer would be? Think about it. 3 to the power of what gives me 3? 1. So you can probably see what's happening here. Once you get really good at this, once you have a bit of practice, what you'll find is you will be able to skip these 2 steps because it will always cancel out. Always, because log to the base of a number of that number is always 1. So the way we would write that as a rule is log to the base a of a always equals 1 no matter what, because you're asking the number to the power of something gives me the same number. The only thing that could be is 1. Hopefully that makes sense. Likewise, if the answer was 1 on and of itself, then of course the answer would always be 0. But anyways, so realistically, in the future, as you start to practice this, you will skip these 2 steps. Which means it is as quick as just using on a calculator. And then of course, on the calculator we can just add this, which if you remember rightly I said was going to be the answer anyway, and it always will be. But at least now you know where that comes from. I'm going to continue doing it this slightly longer way, and I would suggest you do it the same, but you'll start to spot that you can skip these 2 steps. But for now, do it the longer way, okay? Know how to, this is how you learn something. Do it the proper, tedious way, and then over time, you'll gain the understanding and the knowledge needed to use shortcuts that won't screw you over at some point. And it says to 3 sig fig, so 2.33, that's it. Now again, I would like you to have a go at 2 to the power of x. Remember, these videos are not just this passive learning experience. Have a go. Whether that is typing it on a notepad quickly or writing it down on a piece of paper next to you, have a quick go, or at minimum, please think through it. If you just think through the problem, That is practically the same as doing it yourself. It's almost as good. So have a go, think about what you would do. Again, follow these previous steps. Of course, you could do it in one step on a calculator, but I'm going to do it the slightly longer way, and then check your answer. So hopefully through my blathering, anyone that wanted to have a go is starting to have a go. So I'm just going to get started. Again, what we're going to do is apply the log to both sides, and we're going to use the same base as the base for the power. So log base 2 to the power of x equals 32, equals not 32, log to the base 2, 32. Again, use the power law. We're going to bring the x to the front. 2 of 2. Again, log to the base 2 of 2 is going to give me 1, but in case you don't believe me, 1, because log of a number is always going to equal 1. And if we change that to 32, what do we get the answer of? We get 5. Nice and neat. I will also say that in exact form, you can leave it like this. That is something called exact form, okay? Which sometimes your questions will ask you for. You can leave it in terms of logs, just like you can leave it in terms of exponentials, okay? Hopefully those two questions are fine, but we're going to move on to something slightly trickier. You had to know this was coming, right? Surely. We have a bunch of stuff. So, how would you do something along these lines? Well, there's a few things you can do, but first, but certainly not least, is you have to use the power law backwards. Now that might sound a bit weird, but keep in mind, especially in A-level maths, you're expected to use these laws forwards and backwards. So you should be able to break up logarithms into two separate ones, and you should be able to combine them into one whole one. This is actually critical. They're not going to ask you, oh, log AB, what would you write that as? Instead, a solution may hinge on the fact that you need to separate out logarithms, especially when it comes to integration and differentiation in year 13. They will expect you to be able to separate logarithms and also into any kind of form, and it will be critical to the answer. It'll be just a step in the 5-6 mark answer. But why can't I just do this? So what you're probably thinking is, okay, subtraction, I'm going to use the division rule, right? Why can't I just do this? Well, if I write this out in terms of the power law now, that would be the same as having x over 5 squared, which if I square it, becomes this. Okay, that's the answer I get if I use the subtraction law straight away, in the sense of combining them right away. You're going to find that this is actually incorrect. Here's what you're supposed to do, and I'm going to show you why it's different. This 2 here is only squaring the x. It's not squaring the 5. So the first thing you do is use the power law. So we have log 2 x squared minus log 2 5 equals 1. It's also why we didn't just divide by 2, because then we'd still have a number in front of this log 2, the second term. Then when I use the division law, because they're subtracting, we can divide them. Can you see how these are different? Okay, so this method on the right is not correct. Please don't use it. But I see that mistake being used, happening quite a lot. Keep in mind these 2's, because it's squaring, it's affecting just this first thing, not the whole thing. Okay, then what would you do next? Well, this is where things get a lot more fun. In algebra, again, whenever we come across something, we do the inverse function. Now, what's the inverse function of a logarithm? Well, we used before the fact that a power, its inverse function is the logarithm. Likewise, the logarithm's inverse function is a power. So we need to put all of this to the power of something. I know, right? I like to call this exponentiation because it sounds cool. I'm actually not convinced it's the right term. However, I've heard other people say it. So either they've caught on from me or other people like me, but I like to call it exponentiation because it sounds cool. We're going to raise both sides to a certain power. Now, what power do you think that is? Well, if we look back here, the base we used was the same as the base for the power. So use that logic in reverse. The base for our power has to be the same as the base for the logarithm, right? Because again, they're inverses. So we're going to raise this all to the power of 2. And that doesn't mean I'm squaring everything. What it means is I'm putting everything as a base of 2. Like that. Cool. Now that looks heinous, and I don't blame you. To be honest, you can kind of low-key skip this step. This step here is optional. Because once again, once you get kind of comfortable and good at this, you won't need to do this step. All you need to know is that if you put 2 to the power of a log base 2, they functionally cancel each other out, which leaves you with x squared over 5. And what's 2 to the power of 1? It's 2. Times both sides by 5, we have x squared equals 10. So x is equal to plus or minus the square root of 10. That's all you need to have. Cool, right? Hopefully that makes sense. And hopefully you're picking up on it. Again, you can use these shortcuts after time. Okay? Do it the long way first. I know it's boring and tedious, but you need to know what's going on under the hood before you take shortcuts. Whenever you take a shortcut, you should be able to explain to me what steps you're skipping. If you can't, that means you might mess up using the shortcut, because shortcuts don't always work. Okay? Just like in real life, if you take a shortcut getting to school, you should be able to tell me the longer way around, right? Because you know the long route, you know why it's a shortcut. Same principle in maths, and with anything in life, really. So I'm not going to lie to you, we've got like a billion more questions, as you can see from this bar on the side. I'm not sure if I've edited that out or not. We're like a fifth of the way through, so we've got a lot more questions to do, which is fun. So all we're going to do is do them, but they're quite short, relatively speaking. So log base 3x plus log base 3/4 is equal to 2. So of course we need to use the addition formula first. Some people might say, well, why can't I raise this all to the power straight away and do something like this? And then the next step would just be x plus 4 equals 2, right? Because this cancels out. This does not work, because it only cancels when it's the log 3 of everything. In the same way that the square root of 5 plus 4 is not the same as the square root of 5 plus the square root of 4, right? Those two aren't equal in the same way that this isn't. The log base 3 has to be affecting everything. Because there's a plus in between, it's not quite. What you'd actually have to do, so you can do this, by the way, but you'd have to actually combine these into becoming, so what you should actually do is something like 3 to the log base 3 4x. And then so you'd have 4x equals 2, which means x is a half. That would work. So the only order you can change is whether or not you use the power law the addition law first, or you do it after you raise it to the power, okay? So, just wanted to go through those, because I want to go through those misconceptions, because I know, look, I'm going to be honest with you, you're going to make these mistakes, guaranteed. Everyone does, it's kind of a learning experience, but hopefully you'll do it just in your, like, end of unit test, which doesn't matter as much as, like, your mocks, for example, or the real bloody thing. So again, we're just going to go through this. I know I've already given you the answer. Now we're going to raise it all to the power of 3. Why 3? Because the base here is 3. Always copy the base. 4x equals 2. That means these two things cancel out with each other. So we have 4x equals 2. So x is equal to 1/2. Nice and quick, nice and easy. 2 or 3 marks usually. So I find them very useful. But requires practice. So again, I'm hoping you're pausing the video after each one and trying the next one. Okay, don't be passive. Try the next question. So again, speaking of, although the question seems to be different, do the same thing. Have a go, okay? Have a go, have a go, have a go. Don't just wait for me to give you the answer. The best way to do maths in general is to actually do maths. So here it says express as a single logarithm to the base a. This is a very common style of question. Just like in algebra when you did that in year 11, they would sometimes give you this kind of long expression and say simplify fully, express as a single fraction, blah, 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 blah. Same thing with logarithms and powers. So what we're going to do? Well, again, what you're not going to do is do the subtraction rule straight away. Because remember, this 2 is only affecting this first logarithm. You use the power law first. So log a, and that becomes x plus 1 all squared. Now, does it matter that it's log a? Of course not. A is just a number I don't know, so I still treat it as a number. So that just becomes log a. And remember, with the subtraction rule, you're literally just... I'm actually going to put like nested brackets here. All you're doing is dividing them. Wow, so hard, right? Hopefully you're picking this up. Hopefully it's starting to make sense. But I guarantee you, those that are doing this as I'm going along, it's making more sense to you than it is to the people just passively watching, okay? Okay, so something slightly different. We have ln. Whoop-de-doo. Promise you it's not that bad, okay? If you remember, ln is the same as log to the base e. Okay? Now, I want to give you some time to pause the video and have a go yourself, do some active learning. But I'm going to start going now. So if we reimagine this as log to the base e, all we need to do is raise both sides to the base e. Now I'm going to leave it written as ln, and there's a special reason why I've decided to do that. The reason being is writing log e every single time, it's not really done. Like, ln is the mathematical notation, so I'm hoping that as I write ln more and more and more and more and more, you will begin to kind of get comfy with it. So I would recommend that in your head, yes, think, okay, ln means log base e, but write ln anyway. So once again, just like with the normal powers, they cancel. So we have 2x plus 5. Now e to the power of 1, well, anything to the power of 1 is just itself, so I'm just going to leave it as e. So subtract 5 from both sides, and divide both sides by 2. Now, funnily enough, in a lot of questions, you can leave it as just e minus 5 over 2. That's completely valid. You don't need to actually solve it. So this is really quite interesting, because I don't know how nerdy you guys are, but if you ever look at mathematical papers, sometimes they don't even get like number answers. They get something like this, which technically is a number answer. It's just that they haven't bothered writing out what the decimal value is. So this is actually completely fine. But I don't want to push you too much. You can just use, just in case they don't want you to do that for whatever reason, you can either use, there is the e down here, so alpha e, or you can use shift ln and just put e to the power of 1. Both of those are the exact same thing, don't worry about it. Minus 1.14, 3 sig fig, why not? That's completely fine. Especially because the next number is a 0 anyway. Just like so. Again, pretty quick, we're getting through these quickly. So another new type of question. So they might ask you to substitute in a certain value, so a certain logarithm for a letter. And this is really useful as well when you do things like integration and differentiation a bit later on, and maybe even at university if that's what you want to do. So it says, given that y is log to the base 2 of x, find expressions in terms of y for these two things. And you've done something vaguely similar in GCSE, but instead it would say something like, given that y is equal to like x squared, for example, and then write some expression out. So all you really need to do is write this first thing here. So let's write it out as log to the base 2 x squared. All you need to do is write it so that you have log to the base 2 by itself. Okay? So it's not just y squared. Okay? Instead, if you use the power law, you get 2 log to the base 2x, which means it's actually 2y instead of y squared. And that's really a key difference here, because remember, it is still a logarithm. It still behaves as a logarithm at the end of the day. For part B, you might be wondering how on earth could you actually write it as just log 2 to the power of x, because we have 2x here. Well, that is a really good question. So think about it. How can you get rid of that? Well, I could write it as something like log to the base 2 times x. Now, does that give you any kind of hint? Well, it should hopefully bring to mind the kind of power or the product rule. So that is going to be log to the base 2, and again, we're doing it in reverse. So 2 plus log to the base 2 of x. Now remember, when you take the log of a number where the base is that number, it's always going to give you 1. You can check on a calculator if you want, but that's just 1 plus y. And if you notice, there is no x, which is what they mean. When they say find expressions in terms of whatever letter, let's say y, they mean that the only letter that should be in your expression should be y. Having numbers is perfectly fine. So 2y and having 1 plus y are both completely valid in that case. Okay, so now let's get into some spicier stuff. So it says solve this equation, giving you an answer in exact form. And if you look, let me rewrite that just so it's a bit more visible. You have 2 e to the power of y plus 15 e to the power of negative y is equal to 11. Now when I look at this, and it's going to be hard for you to imagine eventually, unfortunately, but it kind of looks like it could become a quadratic equation. Now, you might be looking at this saying, but there's no squared. What are you on about, you crazy man? But if I times the whole thing by e to the power of y, this first thing becomes 2 to the power of e 2y, or y squared, plus 15, and then e to the power of minus y. When I times these, you add the powers, so it becomes e to the 0. And what's anything to the power of 0? It's 0. Now if I shove everything to one side, we have 2 ey squared, well it'd actually be minus 11 ey plus 15 equals 0. Now you have two options here. One option is to simply substitute something in. So you could say, so let's split our page in half. You could say x is equal to e to the power of y, and then your equation becomes 2x squared minus 11x plus 15 equals 0. And that is perfectly fine, you can do that. However, another thing you could possibly do is just solve it, because we use a calculator anyway. So either way, you're actually going to get the same answer. Either way. In one case, you're going to get e to the y equals 2 different things. In this case, you're going to get x equals 2 different things, but then x is just e to the y anyway, so it's the same thing. So either way, let's go through solving quadratics on our calculator one more time. You can use a quadratic formula if you'd like. But if you go down to equation/func, we've got an polynomial to solve. It's a polynomial degree of 2. Number in front of the squared term is 2. Number in front of x is negative 11. The number at the end is 15. So equals once we get e to the y is either equal to 3 or e to the y is equal to 5 over 2. And if you notice, it'd be the exact same thing with x. Now, of course, this isn't actually our answer, because do we care about e to the y? No, we care about what y is. So this is just solving the equation once more. So if we take the natural logarithm, y, because it's base e, so that would be e to the y equals ln 3. So remember, these ln's will cancel out. So we just left with y is equal to ln 3. And since it says leave your answer in exact form, that is our answer. Same thing on the other side. If you follow the steps, you get ln 5 over 2. Job done. Nice and easy. If you did it the x way, again, once you find the solution, you would just end up with this anyway. Another big part of A-level maths is, and this kind of applies to everything, is applying these concepts and formulas and etc. to real life situations. So here it gives us some context. So the decay of a radioactive substance is modelled using the formula N, being the number of atoms after 2 years, is 1000 e to the power of minus kt. So again, very, very standard, very, very common, and I would be very surprised if your actual year 12 mock didn't have a question that was very similar to this. Now, the bright side is that these questions are pretty much always structured the exact same way. The first part, will say, what is the starting number of whatever it is? It could be number of trees in a forest, could be number of rabbits on an island, could be whatever. Then you're going to be expected to work out k, because they give you a value. And lastly, they'll give you another substitution. I've seen a lot of year 12 mock exam papers over the years, and this question almost exactly comes up every single year with a very, very similar structure. So part A, what's the starting number? Part B, they give you some information, work out the constant. Part C, do a substitution. It's almost always the same. In year 13, there are 2 more parts, which is where you're going to be differentiating it. But other than that, the first 3 parts are exactly the same. It doesn't change, which is really, really useful. So, enough preaching. Let's actually go through this. Part A, write down the number of atoms when the substance started to decay. Now, the key part here is to have a look at this and see what's happening over time. So I showed you before, you won't have to do all this work normally, by the way. This is just so I can show you for the first time. When you have y is equal to a positive x, it's an exponential increase, right? You know that from GCSE. Now, in this case, we have a negative power. And what does that negative power do? What it does is it reflects it in the y-axis. So it's an exponential decay. Again, you may know that from GCSEs. So over time, these numbers are decreasing. And does that make sense? Well, from your GCSE science, you should know that the radioactive substance should decrease over time, the number of atoms. So that does make sense. So the starting number is always the number in front of E. 100% of the time. It's always the number in front of E. Okay, nice and easy for 1 mark. Okay, so for part B, it says, given that it takes 14.4 years, very specific, for half of the substance to decay, find what K actually is. So, if we write out this formula, we have N equals 1000 e to the minus kt. Now, they've actually given us quite a bit of information. First of all, they've given me that t is equal to 14.4. They've also given me that n is half of the substance. So half of 1000 is 500. So from here, we can most certainly work out exactly what's going on, because we have only one unknown. So that'll be 14.4k. So divide both sides by 1000. 500 over 1000 would just be a half on the left hand side, is equal to e to minus 14.4k. Now we're going to use the natural log on both sides. So we have ln of a half equals, I'm going to write it out fully, but again, remember you can skip this step. So in other words, we have ln a half equals minus 14.4k, which means k, once we move it over, is just ln of a half over minus 14.4. Just like so. And does it say to give it exactly? No, 3 significant figures. So all we need to do is put this into our calculator. So go back to calculator mode, press 1. We have ln of half over negative 14.4, which gives us an answer of 0.0481 to 3 significant figures. And lastly, what does the last thing say? Well, it says, calculate the number of atoms left when t is 30. That's simply just subbing into this formula with k and t. Easy. So n is equal to 1000. E to the minus k is 0.0481. And t is 30. So let's put this into the expression. So we have 1000 shift e minus answer times 30, which is 235.968. Now, since these are the number of atoms, we should definitely round this to the nearest whole number, because you can't have 0.968 of an atom. So that's just going to be 236 to the nearest whole number. So if we look here, we have a very similar question. Now at the part C, it is a substitution, but you're substituting in for t, not for t. That doesn't make any sense. For capital T, not for lowercase t. So it is, again, just a substitution, except it's a bit harder. So for the first part, we obviously cannot do this part, because rate of change, you will find, is going to be synonymous with differentiation. Okay? So all we need to do is do parts B and C. So start with part B, find the value of K. Well, it says after 5 minutes, the temperature is 70 degrees Celsius. So capital T is 70. Equals 75 e to the minus k, and that was 5. So if you want, you can write this as k times 5, or you can write this as 5k plus 22 minus 22 from both sides gives me 48 is equal to 75 e to the minus 5k. Divide both sides by 75, we have 48 over 75 equals e to the minus 5k. Now, all we need to do is natural log both sides in order to get rid of the e. So, as I said before, you can start using the shortcut of just skipping straight to this step because it's going to give you the same answer either way. So it does seem like a lot of work for a 3-mark question, but it's not that bad, especially compared to some of the other stuff you're going to be expected to do in later topics. Not to scare you, of course. So natural log, fraction again, 48 over 75 minus 5, can be 0.089. And then here it says find out how many minutes it takes for the water to cool to 55 degrees. So I'm actually going to go back up here. We have the final temperature. I mean, essentially it's the same as part 1, by the way. So 55 degrees equals, it's effectively the same thing, except instead of working out lowercase t, we're actually working out, lowercase k, we're actually working out lowercase t. Now, I'm actually going to leave k as k because I've saved the value on my calculator and I don't want to bother writing out each time. But we're essentially going to follow the exact same process. So minus 22 from both sides, we get 33. Divide by 75. Natural log. Minus kt, and then we're working out what t is, so we literally just have the exact same thing, but instead of t on the bottom we have instead of t on the bottom we have k. So over minus k, which we can put straight into our calculator. So what I'm going to do is I'm going to just edit these values. We have 33 over 75, and that is over negative ans. Gives me an answer of 9.20 minutes. So what I'm going to do, what I like to do is write 9.20 minutes to 3SF. But then since it says the number of minutes, I would then also round it down to nearest number. Either way works, okay? Okay, so moving on to a very big part of A-level maths, as we've seen before, is basically sketching and finding out the ranges and domains of functions. It comes up with pretty much every single new graph that you have, and it comes up extremely frequently as just parts of questions. So there was actually a part C to this question, but again it involves differentiation and integration, so obviously we're not doing that yet. So part A, when it says the range, that means all of the values that come out of the function. So in other words, it's all of the y values. Okay? So the best thing we can do is actually sketch what the graph looks like. Now, first of all, what will this graph look like, the ETX graph? Well, the ETX graph normally just looks like this. Yeah? So if, and remember there's an asymptote at y equals 0. Now, I know that there are two things affecting x, but do we care about x? We're talking about the range. So we don't care about these x things here. So it means we only care about this minus 3 on the end. And what would that do? Well, it shifts the entire graph down. So instead, it's going to become a graph that's something like this. Okay, where this is our new asymptote. Because again, everything has been shifted down. So what are the range of values, that's what the range means, that this function can take? Well, it's anything that's bigger than minus 3. So the way you'd write that is you'd write f of x is bigger than minus 3. And you should ask yourself, can it equal minus 3? So do I put an underline? The answer is no, because remember, these graphs never touch their asymptotes. Okay, they never cross them. So hopefully that makes a bit of sense. With those questions, you should always draw out the function and have a look at what's happening. Part B says find the exact coordinates of A and B, where A is the y-intercept and x is the x-intercept. B is the x-intercept. So let's start with the y-intercept. How do you work out the y-intercept? Well, all you need to do is sub in x equals 0 into your expression. And if we got our calculator out, that is actually going to be very, very easy for us to do. So x equals 0, let's sub that in. We have e to the power of 0 plus 1. So we have e to the power of 1 plus 3. Sorry, minus 3 even. Minus 3. And if you notice, it's telling me to give the exact coordinates. So can I simplify this? The answer is no. Instead, I'm just going to have e minus 3. So what are the coordinates of a, where it crosses the y-axis, this point here? It's going to be, so a is going to be 0, and then e minus 3. Okay? And it looks like it is down here, which it is, right? So we should get a negative value. And if you do e minus 3, remember e is approximately 2.7. 2.7 minus 3 is indeed a negative number, so that actually works beautifully. And as for b, that should be somewhere over here. So we have a here, we have b here. But how do we work out x-intercepts? Well, all we need to do is sub in y equals 0. So what we're going to do is we have e to the power of 2x plus 1 minus 3 equals 0. So e to the power of 2x plus 1 minus 3 equals 0. So let's add 3 to both sides. We have e to the power of 2x plus 1 equals 3. Now we need to take log to the base e of both sides, so ln both sides. If I do that, the e goes away, and on this side it becomes ln 3 minus 1. So we have 2x is equal to ln 3 minus 1. And then divide both sides by 2. So we have ln 3 minus 1 over 2. Very ugly answer, but it is the correct one. So for coordinate b even, we have ln 3 minus 1 over 2, comma 0. Beautiful. Another major part of A-level maths is applying these new functions to real-life situations. So in this case, we have a log function, okay, and it's in a real-life kind of scenario where we are comparing the resting heart rate of a mammal compared to its mass. So this is, again, a real-life example, and they expect you to be able to do things like interpret the value, comment on the suitability, and things like that. But fortunately, these last two parts aren't that bad. They do actually work. So, how are we going to do this? So if we read this question, it gives us a normal power law. It gives us an actual exponential equation here. But if you notice, we have a straight line graph. Because what they've done is they've taken the log of both sides. They've changed this from an exponential equation into a log equation. That is very, very common. If you do A-level physics, you're going to do this a lot, especially in your experiments. Because if you think about it, an exponential increase or decrease in this case is quite difficult to read. So it looks something like that. That's very difficult to work out the gradient of. It's very difficult to pick off certain values, whereas a straight line is beautiful. Okay, it's really easy to find the gradient of, to find interesting points on as well. Okay, so that's essentially why we do it. If you have a look, it says find three significant figures, the values of p and q, so these two things here, and it tells us that the y-intercept of this graph up here is 2.25 and the gradient is minus 0.235. Now that implies it's a straight line, equation of a straight line, but this is not the equation of a straight line. This is what we're going to do. We're going to take the logs of both sides and make it into this form right here. Here is a top tip for you. If you have an exponential equation and you take the log of it, it always becomes a straight line. That's actually a way you can test if something's exponential, which again, if you do A-level physics, then you're going to do that. You're going to test if things are exponential or not. Because if you take the log of them and they give you a straight line, they are exponential. If you take the log of them and they don't give you a straight line, it's not exponential. So let's take the log of both sides of this equation. And because it says log to the base 10 here, we're going to take log to the base 10. But remember, log to the base 10 is the same as just writing log. So I'm just going to write log because I'm very lazy. So we have log h equals log. I'm going to put this in brackets just because it looks a bit nicer. Let's put this in brackets as well, just so you guys can see what I'm doing. We're going to use the power law to bring the q to the front first. So we have log h equals q log pm. Now we're going to use the product rule, or the multiplication rule, the addition rule, whatever you want to call it. Because we have two things timesing each other, we can separate them out. But remember, this q has to go with both of them. Now, if I look at the kind of question here, log m is what x is. It's the variable. We're varying m. We're not varying p. So I'm going to put the m first. So we have log h equals q log m in brackets plus q log p. So now if we compare this to y equals mx plus c, our constant is q log p. Our variable is log m, which if you look, it says here illustrates the relationship between log h and log m, so that's good. Y is log h, again, that fits, right? These things here should be y and x, our variables, which means the gradient is q. So if I look at this over here, it says it has a gradient of minus 0.235. So in other words, m is minus 0.235. So in other words again, q is minus 0.235. Because it's equal to m equal to the gradient. Hopefully that makes sense. Now for the next bit, it also tells us that it meets the axis at 2.25. Remember, that's what c is. So we now know that q log p equals 2.25. And if you remember, we also know what q is. So log p, if I divide both sides by q, equals 2.25 over q, which is equal to 2.25 over minus 0.235. Now you might be tempted to just do this now on your calculator. I'm going to leave it for now because the next thing we need to do is get rid of the log. Now remember, log is log base 10. So we need to raise both sides to the power of 10. So if I do that, I get p is equal to 10 to the power of 2.25 over minus 0.235. Does it say the exact value? It says 3SF. So all we need to do now is type it into our calculator. I hope that makes a bit of sense. I did go through it a bit faster just to show you how quickly you can actually do it once you get a bit stronger, but hopefully you managed to follow along. If you didn't, leave a comment and I'll let you know. And it says to 3SF, so 2.66 times 10 to the minus 10 would be what we're doing here. And that looks a bit weird to me. So what I'm going to do, just to check my answer, I'm going to put this in brackets. Just to double check. Yeah, perfect. That is correct. Wonderful. Hopefully that makes sense. And that is to 3SF because remember, standard form, it just counts the significant figures. So that's it for part A, which is interesting. So for part B, it then says, a particular mammal has a mass of 5 kilos and a resting heart rate of 119 beats per minute. Comment on the suitability of the model for this mammal. So what we're going to do for part B, and I'm going to write the answer up here even though it looks a bit weird, is I'm going to sub these values into this equation here. The other thing you can do, by the way, is actually sub it into this equation here. So we now have a new log equation. So log h equals minus 0.235 log m plus q, which is q, which is minus 0.235. So I probably should have left that as that. Log like that. So if you sub in these values, it might come up with something that is incorrect. So again, you can sub it into the first equation or sub it into the last equation and then check and see what happens. So let's have a go at that. So just for interest's sake, let's just sub it into the logarithmic equation. So we have h, which is 119. So because we want to check if they're the same, right? So what we should do is find out what the log of 119 is, and then also sub in this side over here. So minus 0.235 log m, which was 5 kilograms, yeah. So the reason why I decided to use the logarithm one is because A, I wanted to show you how to sub into logarithmic equations, but also B, it is usually good practice if they give you some kind of choice to actually sub into the equation that you form yourself. So if I sub in what log of, this was 119, right? Yeah, 119. So log is shift this button. It's 2.0755, okay? In fact, I'm going to write the whole thing out. 5, 5, 4, 6, 9, 6, 1. And let's work out what the opposite side is. So, and what we can do then is literally just compare and see what they are, how similar they are, right? 5 minus 0.235 log 2.66 times 10 to the minus 10. That should be fine. So we have 2.0 blah 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 0 8 5 8 9 4 8 6 4. If you have a look at these two numbers, they're pretty close, right? Like 2.07 versus 2.08. And if we round them, it's 2.08 compared to 2.09. So if you wanted to, you could round to 3SF. So 2.08 3SF compared to 2.09 3SF. Comment on the suitability. It is suitable, as they are close. Remember, and this is something that people really need to remember just in real life, this is a model. It is not an equation that 100% guarantees you'll get perfect answers. Instead, it gives you an approximation to what is reality. Even things, and a lot of rules in science follow that kind of mindset where it won't be exact. So where we use, for example, exponentials, and we used it a bit earlier on, do you remember the formula for radioactive decay? Where it said there was a number, and let me just try and find it, this. And it says the number of radioactive kind of particles that are still there. If you have, I don't know if you spotted this, but one, it gave us decimal numbers. That can't be right. And two, it never reaches 0, which means it will never actually fully decay according to this. It's a model. It does follow an exponential relationship, but yeah, we're right. Like eventually all of them will be gone. And obviously it won't give us decimal answers. They're models. So in my opinion, this is actually pretty damn good. It's pretty good. And remember, this is a logarithmic relationship, so these are really close to each other. However, you are fine in saying it's not suitable as the values are different. Both answers are correct. So you might think, well, hang on a minute, could I just always write it is suitable versus it's not suitable? No, you would get 0 marks. You need to show that you've done some deduction, some working out. Okay, so if you did all of this, this will give you 2 of your marks. If you then write it is suitable or it isn't suitable because they're close or because they're too far, because they're not the same, that will give you the final mark. So you can say not suitable. If they ask you for your opinion, which is what they're doing, right? Comment on the suitability. You're allowed to say it is or isn't suitable. Always. You just need to back it up. You need to have something here that's telling you like why. Why does that make sense? Why is that the case? If you have that, you get the mark. Period. Done. But you can't, unfortunately, just go through the exam paper and just guess suitable, not suitable, suitable, not suitable, and get a free mark for nothing. You have to put something down. Unfortunately. Lastly, it says, with reference to the model, interpret the value of the constant p. So they love doing this. Essentially, with reference to the model, so what are they modelling? They are modelling the beats per minute compared to the mass of the mammal. Okay? That's what they're comparing. And we have to comment on the constant. It's such a common question, it always comes up. So what are these constants? That is a really good idea. Again, if you're into science or you do physics, you will begin to get a lot better at this. But in general, this is how things come up. Scientists figure out a mathematical relationship between them. So if they see a graph, if they plot a graph and it goes like this, what they might say is h is proportional to mq. Because that's what they can say. They know that it follows an exponential relationship. What they don't know is what that relationship looks like. Now, what happens in GCSE when we have this proportional sign? We introduce a constant, right? That is exactly what P is. Do you know F equals ma? Same thing. Isaac Newton knew that F was proportional to A, so he introduced a constant, m. Hooke's law, F equals kx. Again, this is a constant. It started off as force is proportional to extension. So, all of these come from proportionality. So again, hopefully that's just from GCSE. So what is this constant P? Well, you can't just say it's a constant because it says with reference to the model. So what's the relationship between all of these constants that we have in life? So the m in F equals ma, the k in F equals kx. Here's what they are. They are conversion factors. That's what they are. Okay? So, just so we're clear, P here is you can call it a constant of proportionality. That converts between and then your two variables. So the m in F equals ma converts between acceleration, A, and newtons, the force. F equals kx converts between x, the extension, and F, the force. In this case, what is it? Well, what is m? It converts between the mass of the mammal and the heart rate, resting heart rate. That is what every single one of these constants of proportionality are. They're conversion factors. All of them. They're constants as well. Hopefully that makes sense. F equals ma is kind of a bad example, by the way, because mass does change. What I'm referring to there, because I know someone's going to mention it, is that for a specific object, force is proportional to acceleration. So the mass is constant in that regard, okay? But for Hooke's law, for example, the spring constant is different for different materials and things like that. So I hope that makes sense. In order to get this last mark, it is the same answer in every single one. If you guys followed me from GCSE, you know that I gave you, when we did those real life examples, I told you exactly what to write for gradient questions, where it was the rate of change of this with respect to this. It's the same concept. All you need to do is say it is a constant of proportionality that converts between whatever your independent variable is, so your x, so in this case m, and the whatever your y is, your dependent variable. That's it. That's all you have to do. All you have to do. So, sorry, it's independent and dependent. So m is dependent and h is independent in this case, because the one that you change is the independent variable. So we change the mass in this case. That brings us to the end of this extraordinarily long video. It is a brand new concept, it's a brand new topic as well, so I would encourage you to, again, attempt this worksheet within 24 hours, let's say, 48 at an absolute push, and also find other questions as well. I haven't answered every question, I've answered every style of question, but they can obviously throw curveballs at you. But we will go through more exam questions later on. So just so we're clear, I have picked out exam questions, but I'm not doing every exam question because then we'll have nothing to do towards the end of the year, okay, when we do exam papers. But hopefully that all makes sense. Again, I've left the links to everything in the description, the worksheet, the Patreon for the statistics course and mechanics course, the playlist for all of the A-level videos, and of course my email address if you are interested in asking me about tuition, and the Discord link where you can join all of your fellow colleagues in talking about stuff, and also ask about tuition if you'd like so. But without that, I hope you have a truly wonderful day.